right, so next up we've got epoxidation, and then after that, anti-dihydroxylation. And so epoxidation means the formation of an epoxide. An epoxide is a three-membered ring with two carbons and an oxygen, right? This is what an epoxide is. And this is, in fact, like if you think about like epoxy resin, that's what this stuff is made out of. It's made out of these epoxides that then polymerize and then harden into the hard stuff, right? And then, of course, anti-dihydroxylation means that we're going to add OHs, right? Dihydroxylation. And then, of course, you can think about it as anti to one another. And so this is done with alkenes, of course, and with peroxy acids. So peroxy acids are like a carboxylic acid, except we've got a peroxide in there as well. The most commonly used one is Mcpba, and that stands for metachloroperoxy benzoic acid, right? So that's the name right there. You'll just see this Mcpba as a reagent. Here's the drawing of it, if in case you're interested in. The meta here just refers to the positioning of these two substituents on this benzene ring. The chloro obviously stands for that there's a chlorine here. The peroxy stands for this peroxide right here. And then the benzoic acid corresponds to the rest of this molecule, right? We've worked with benzoic acid in lab. You can see that we've just added an extra oxygen to make it a peroxy acid. And so what occurs here is we have our alkene and a slightly complicated looking concerted reaction here. So I'm just going to put R for the benzene ring with the chlorine on it, right? And so this occurs in one step. That's what concerted means. And so the first thing that happens is this alkene attacks this oxygen. This oxygen-hydrogen bond then attacks our carbon. This oxygen-oxygen bond breaks over here to make a double bond. And then this double bond goes over here and picks up this H. And so you get this transition state that looks something like this. Right, where all these kinds of bonds are being broken and formed all at once. So I've color coded it so you can see what kind of bonds we're going to form and break. So let's go ahead and take a look at this, because it is quite confusing to look at first. So we can see that our purple bond results in a carbon-oxygen bond, as does our orange arrow, right? So those are those two bonds right there. And then we actually break off from this molecule. We see that we form this double bond from these blue electrons. And then we form an OH bond using our green arrows. And so you can see that we've formed an epoxide here. And on the other side, we've reduced our peroxy acid down to a carboxylic acid. And so there's the epoxidation step, right? We formed an epoxide there using Mcpba. This is often followed up by adding an acid. So something like H3O plus, right? This is called acid catalyzed. And so the first thing that's going to happen here is we'll have our epoxide. And this thing's going to go ahead and pick up an H plus to protonate itself. And then we have some water floating around here. So this water will nucleophilically attack our epoxide, very similar to the brominium and to the macronium ion, right? You see these are overall very similar mechanisms. And so, of course, they're going to add anti to one another. And then finally, we have a proton transfer. So we're going to deprotonate our alcohol that's currently protonated to get our final product. And we can see we've added 2 hydroxy compounds anti to one another. And so overall, the reaction is we add our alkene. In the first step, we add the Mcpba to form our epoxide. And then in the second step, we simply add some aqueous acid to get this anti-addition. And of course, we get the enantiomer as well. And similar to the other reactions, you can use different nucleophiles, right, such as alcohol, right, maybe ethanol, and then amines as well. But you can see, although we're learning a lot of reactions, very many of them have similar steps. In this case, this acid catalyzed epoxide ring opening.